Well, since our logarithmic function is an inverse of the exponential function, we should make sure that we state certain properties that are always true regardless of the exponential function that we're talking about, or logarithmic function that we're talking about. Okay. For one, we always know that this is the kind of function where the logarithm base a of 1 is equal to 0. In other words, on the basic function itself, no shifts, no translations, or anything else, it will be the kind of graph that passes the point 1, 0. Always the case. Number 2, we stated that whenever we took a logarithm base a of a, we should get 1. So in other words, whatever our base is, if that is the x value in our logarithmic function, then the result will be a y value of 1. So our graph should pass through the point a1. Finally, and I say this is true about all logarithmic graphs, I'm looking at graphs, I'm taking advantage of the property that says logarithm base a of a to the x is equal to x. Well, I don't want you to get too wrapped up in that x business, but for example, we could state that if we were to take a logarithm base a of 1 over a, we should always get negative 1. So in other words, the point 1 over a, negative 1 is always a good point for us to get on our function. 1 over a, negative 1. Okay, now, a couple other properties about the graphs that are always true that we should be able to take advantage of. For example, whenever we take a logarithm, base a of x, x must be greater than 0 by definition. In other words, whatever the argument is, we set the argument greater than 0. Now we'll see that's important later when we start talking about shifts and translations, but our argument must always be positive. You can only take the logarithm of a positive number. Fifth thing, for all logarithms, there is a vertical asymptote. Trying to print here is kind of difficult. The vertical asymptote is always given at x equals 0. In other words, wherever the argument is equal to 0, then we have a vertical asymptote. We have a vertical asymptote here at x equals 0. Okay? So this will be true. This graph will always take this sort of form. Now, we should be aware that what happens if that base is less than 1? Well, then what's going to happen is that this graph is going to flip. For example, if I told you I wanted to find the graph of y equals logarithm, I'm going to try spelling logarithm here. Y is a logarithm with a base of 1/2 of x. What will happen? Well, we could say that, for example, at x equals 1/2, by the properties above, y would equal 1. We could say that when x is equal to 1, y would equal 0. And we could say that when x is equal to 2, y should equal negative 1. Why is that? Well, again, let's go to our property right here, 1 over a. So 1 over 2, its logarithm of 1/2 is negative 1. So let's see what happens. This graph would actually end up looking like this. And that's because the base is between 0 and 1. So if you have a base for which that's true, well, then we should be careful to make sure that we know that that if the base is between 0 and 1, we'll have that reversed look right here. One more note right here, whenever the base is 10, we never really write log base 10 of x. Right? What that is always written at as is logarithm of x, and that's called a common logarithm. So if no base is indicated, and we just write log, then be aware that what's being implied is that the base is 10. We call it a common log because this number 10 is very common to our number system, so it becomes an important thing for us. Okay, more to come.